In this video, we're going to take a look at very small concentrations. Now, just because concentrations are very small, it doesn't mean that they're not important. Many times, a tiny concentration can lead to disastrous effects, especially if there's something that's very toxic. Or sometimes you don't want to overdose on anything, and you only need small amounts of certain vitamins and nutrients. And so you'd have to pay attention to those concentrations, even though they're very small. Now, we do have a different unit for concentrations that are extremely small. We often see this in the medical field and environmental context. And we call those units the ppm, ppb, and ppt. So parts per million, parts per billion, and parts per trillion. And so basically, you can see all the different formulas over here. We just do the mass of the solute over the mass of the solution times a million for parts per million, times a billion for parts per billion, and times a trillion for parts per trillion. So 10 to the power of 12, 10 to the power of 9, 10 to the power of 6 for ppm, ppb, and ppt. And so you can take a look at what ppm and pp, all these actually mean in terms of concentration. So if we had 1 ppm, that's like almost saying 1 drop of something in a bathtub full of water, or like 30 seconds out of a year. That's how small of a concentration that is. If we had 1 ppb, that's like 1 drop of something in 250 full barrels of water, or 3 seconds out of a century. If we had 1 ppt, that's like 1 drop in 20 Olympic-sized pools. So that's a lot of water there, or 3 seconds out of 100,000 years. So very, very small, but still can be significant, especially in environmental and medical context. So let's take a look at some examples as well. So if we look at a water bottle, so a water bottle label will have a lot of concentrations listed in ppm. So you'll see sodium ions, we'll say 36 ppm. And you'll see the same thing for, we have lead over here, for example, 36 ppm. Well, this one's a bit different. We have 42 for sodium here, and then lead is 0, which is good. We don't want lead in our water there. So sodium is 42 as opposed to 36. Magnesium would be 36 ppm. But either way, you can see the ppm there written down. And what that basically means is that if you had, let's say it said 36 ppm, it would mean that you have 36 parts of sodium for every million parts of solution or water overall. So that's a very small amount, a very small concentration, but it is significant for dietary reasons. So it's almost like a percentage, but rather than being per 100, we have, per million, for example. So you can almost think when you do 100%, that'd be almost like per 100 essentially. So pph. So it's the same idea, just more particles present in that scenario because we have very, very small concentrations. And again, small values do matter. So take a look over here. We have nitrate levels in aquariums we're looking at. So at 100 ppm, fish become stressed. And again, that's a very low concentration. Below 10 ppm, that will slow the growth of algae. Ideal level is about 25 ppm. So we give you these concentrations because even though they're very low, they do matter for living things in aquariums, in actual ecosystems that are natural ecosystems. So they are important even though they are small. So do remember that. So we're going to do some examples of parts per million, parts per billion, and parts per trillion. So let's go ahead and see if we can fill in some blanks first. So in medical and environmental fields, concentrations are often extremely small, but they're still important. So when we have these very small dilute concentrations, we're going to express them in parts per million, which is ppm, parts per billion, which is ppb, and parts per trillion, which is ppt. Almost like a percentage, but instead we have million, billion, and trillion that we multiply it by. So let's go ahead and try our first example for ppm out. So symptoms of mercury poisoning become apparent after a person has accumulated more than 20 milligrams of mercury in the body. Express this amount as parts per million for a 60 kilogram person. So the 60 kilogram person, that's our solution. This is our solution here. It's our massive solution. Now, the masses that you use in your formula, so for example, ppm, they need to be consistent. So massive solute over massive solution times 10 to the power of 6 times a million, because we're asking ppm here. Now, this is in kilograms right now. So I need to make sure these are both consistent. I can convert one to kilograms or the other to milligrams. I can convert them both to grams. It doesn't really matter as long as they are consistent. So let's just practice our unit conversions here. Remember that if we have 1 gram, that's 1,000 milligrams. And if you have 1 kilogram, that's going to be 1,000 grams. So I'm going to convert these both into grams. So first I'll do my 60 kilograms times 1,000 grams per 1 kilogram. Cancel out kilograms, and you'll get 60,000 grams. And then for my mercury, I'm going to do 20 milligrams times, we have 1 gram for every 1,000 milligrams. So cancel out milligrams. In other words, I'm dividing by 1,000, and I get 0.02 grams. So 0.02 grams there. And I have to keep the same number of sig figs, so it's 1 sig fig each, so I'm good with that. So now I can do that my ppm is equal to the 0.02 grams over 60,000 grams times a million. So 0.02 divided by 60,123 times 10 to the power of 6, which is a million. And we get 0.3333, keeps going, ppm, which is approximately, to 1 sig fig, 0.3 ppm. So that there will be your answer. When you're done your practice problems, you can always go back and double check your work to make sure you're on the right track. Let's just find that question that we did here. So I can go to the answer key over here and take a look to see if I did that correctly. You always want to check your work. You always want to check your answers, because you may have made a mistake and you want to learn from those mistakes. So I'm just going to scroll down until I find that question. Looking at ppm and ppb, I thought I had it here. Right here. Okay. Yep. 0.3 ppm. So we're on the right track with that. Perfect. So we can go ahead and try the next part of that question. So express this amount as ppb instead. So it would be a similar idea. We already did our conversion, so we're fine. We have mass of solute over the mass of the solution times a billion instead of a million, 10 to the power of 9. So that would be ppb is equal to 0.02 grams over 60,123 grams, 60,000 grams times 10 to the power of 9. So we'll have 0.02 divided by 60,123 times 10 to the power of 9, and we get about 333.333, keeps going, ppb, which is approximately, to 1 sig fig, 300 ppb. And once again, you can go and check your answers. So for part B, 300 ppb to 1 significant figure. We're on the right track. And lastly, we're going to do the same thing here, but we're going to express it as a mass percent, just to show you why we use ppm and ppb for something like this. I mean, this is a really tiny amount of solute in a really large mass, so it's very dilute, but it still does matter, because mercury is very toxic if you go above certain ppms or certain ppb values. So you might often look at those values if you're eating fish, sushi, for example, and choose your fish based on that, because it can lead to toxicity. So remember that percent mass was, so percent mass is the mass of the solute, which is our mercury, over the mass of the solution times 100%. And so we're going to get 0.02 grams over 60,000 grams times 100%. And that's going to give us, so let's go ahead and try it out, 0.02 divided by 60, 60,000 times 100. And we get 0.000333333%. Such a small percentage. This is not very meaningful to us, written as a percentage that way. So that's why it's better to use ppm or ppb for this scenario. But let's go ahead and round it to the proper number of sig figs, 1 sig fig again. So 0.12343% mass for that situation. Let's go ahead and try our next example over here. Determine the ppm concentration of a solution in which 3.49 grams of toxic mercury ions are dissolved in 800 mils of water. So we need to be careful with a question like this. So in this question, we need to know that we have ppm is equal to the mass of the solute, which is our mercury, over the mass of the solution. Now, there is an aside here. The mass of the solution, don't forget, is the mass of the mercury plus the mass of the water. So it has to be mass of water plus mass of mercury. Now, since it's such a tiny amount, it won't make much of a difference in our calculation, but it's still important to note that. So remember, our mass of water is 800 liters here. Our density is 1 gram per 1 mil. So if we have 800 liters, that's 800,000 mils. That's 800,000 mils, which is equal to 800,000 grams. So that's a tiny amount of mercury in that big amount of water. But let's go ahead and find the total mass here. So we have 800,000 grams plus the 3.49 grams. So you're doing your 800,000 plus 3.49. And you can, again, if you're nervous about making mistakes during your test, you can use your calculator even for simple stuff. And we get 803,000. We get 800,000 3.49 rather. So 800,000 3.49. And so this would be our total mass here. And I think I made a mistake with how I wrote it down. 0.49 grams. There we go. So now we can use that as our mass of our solution. So we can go ahead and do this. Our ppm is going to be equal to the mass of the solute, mercury, 3.49 grams, over the mass of the solution, times 10 to the power of 6. So 3.49 divided by that times 1,000,000. And we get approximately 4.362480969 ppm. It looks like we have 3 sig figs is our smallest number of sig figs, 3 sig figs. So to 3 significant figures, that would be 4.36 ppm. And then you can make a therefore statement. So therefore, the concentration is approximately 4.36 ppm. And again, that was the 3 significant figures. So you can see there's additional practice problems for the percent VV, MM, MV, and then you can also see some practice problems for ppm included here as well. So you can try those out, and the answers are included off to the side there. If you go back to your presentation that we were looking at earlier, our slide deck. There's some practice problems here, some pause, try, play videos for the parts per million, parts per billion, and trillion. So you can try those out. They give you a different perspective. And then here we have our summary table for the different measurements of concentration that we saw in this overall lesson, a description of where they'd be applied, along with their formulas. Again, this table shows mass as weight, but it's the same concept, same formula, and then again, same applications that we discussed previously. So you can try additional practice problems in your learning goals area. So when you click on Unit 4 Learning Goals, you can go there. And if you go to the concentration of consumer products, you'll see a worksheet with some practice problems, including a variety of the different concentrations there.